to be talking about linear systems, Gaussian elimination, Gauss-Jordan elimination, the rank of a matrix, and pivot points of a matrix. It is simply a set of equations with two or more unknown variables. For example, 2x plus 3y equals -8, 5x plus 2y equals 3z, and 4x minus 2 equals 3y plus 4z. You may have seen something like this before, where you used elimination or substitution to solve for x, y, and z. And note that in order to solve for x, y, and z, because we have three variables, we need three independent equations. If we only had two equations given, but we had x, y, and z as variables, we would automatically know that we are not able to find a solution to the system. Gaussian elimination is one way that we can use to solve a system of equations. And by the way, when I mean solve the system, I mean find the values of x1, x2, and x3 such that the left side and right side of all three equations are satisfied. Also note that I lined up x1, x2, and x3 under one another. It will probably be easier for you to make sure and rearrange your equations in advance. In this case, my equations are already rearranged. My x1s are here, my x2s are here, my x3s are here, and all my numbers are on the right-hand side. First step of Gaussian elimination is to put our system of equations into an augmented matrix. What that means is we are going to list all of our variables in order, followed by the constants. We're going to put a little line here, which kind of acts as the equal sign, and put our constants first, exactly as they're shown. Next, in each row, we're going to fill out each equation one by one. The very first equation does not have an x1 value, therefore it will get 0 as a placeholder. Next, we're going to put the coefficient in front of x2, which is a 2. We are going to try to use matrix operations to reduce this matrix down to row echelon form. Row echelon form is simply abbreviated as REF. Let's talk a bit about the different matrix operations that we can do. We can swap rows, we can multiply a row by a constant, or we can add rows to one another. So the first step that I'm going to do is to swap rows 1 and 2. So the way you're going to label your rows, top row is row 1, second row is row 2, third row is row 3. So all you do is simply put all the numbers in the first row down into the second row, and all the numbers in the second row up into the first row. So the next thing you want to watch out for is, can you add any rows together? Can you multiply any of the rows by a constant, which can be a whole number or a fraction, which is why we don't have division when it comes to matrices, because you're able to multiply by fractions as well. Or can you swap any rows? So the next step that I'm going to do is take row 1 and add it to row 3. So row 1 will stay the same. Row 3 is the one that's going to change. 1 plus -1 is 0. -2 plus 1 is -1. -3 plus 2 is -1. And 0 plus 3 is 3. Now this is our new row 3. So with Gaussian elimination, we want to obtain zeros below the diagonal, and all of the numbers in the diagonal should be 1. So what I'm going to do is swap rows 2 and 3 so that this 1 can come up here and be part of the diagonal. So when I swap them, the zeros will stay the same. This will be -1, this will be 2, and the 1 and -1 here are also going to switch, and the -8 and 3 are going to switch. So now I have 1, -1, and +1 down my diagonal. Now all I need to do is make this -1 into a +1 and eliminate the 2 and make it into a 0. And then we will have row echelon form and can solve our system. So step 4, row 2 times 2. And what we get when we do that, well, row 1 and row 3 stay the same. Row 2 becomes 3 times 2, which is 6 here, negative 2. Now for step 5, I'm going to add row 2 to row 3. So row 2 will stay the same, but row 3 is going to have addition done on it, and we can get this value down here to become a 0. So when I add row 2 to row 3, 0 plus 0 is going to be 0. Negative 2 plus 2 gives me 0. Negative 2 plus 1 gives me negative 1. And 6 plus negative 8 will give me a negative 2. Now this is the matrix that we're left with. We still need to change this negative 2 to a 1 and this negative 1 to a 1. So what I'm going to do for step 6 is negative row 3, meaning multiply negative 1 times row 3. So what we get when we do that, 0 times negative 1 is 0 for both of these. This will become a positive 1, and this will become a positive 2. For step 7, I'm going to multiply row 2 by negative 1/2. Negative 1/2 times everything in row 2 will give us 6 times 1/2 is 3, and times the negative is negative 3. 2 times negative 1/2 is going to be 1, and this negative 2 is going to be 1. So the final matrix that we end up getting, 0, negative 3, 2, 1, 1, negative 3, negative 2. Now this matrix is in row echelon form because we have 1s along the diagonal and 0s underneath. Continuing with the steps of Gaussian elimination, we need to put our matrix back into a system of equations. So let's start with the first row. 1 means we have a 1x1, minus 2 means minus 2x2, minus 3 means minus 3x3 equals 0. For the next row, we have a 0. For the last row, we have a 0x1, a 0x2, so we can leave those out, but we have a 1x3 equals 2. Now that x3 equals 2, we can back substitute it into this equation. x2 plus x3, which becomes x2 plus 2, equals negative 3. When we move the 2 to the other side, we get negative 3 minus 2, which means x2 is negative 5. Now we back substitute these into the first equation, and we get x1 minus 2 times x2, which is negative 5, minus 3 times x3, which is 2, equals 0. Now x1 plus 10 minus 6 equals 0. So our solution to this question is x1 equals negative 4, x2 equals negative 5, and x3 equals 2. We could have also solved this using Gauss-Jordan elimination, in which case we don't have to back substitute. This method is almost the exact same as Gaussian elimination. However, with Gaussian elimination, we put our matrix into row echelon form where we had 1s along the diagonal and 0s underneath. With Gauss-Jordan elimination, the only difference is that we need to have 0s above the diagonal as well, so that we don't need to back substitute when we revert our matrix back into a system of equations. So the first thing I'm going to do is multiply row 2 by a 3. And I'm just going to write what's going to happen over here. 0 times 3 is 0, 1 times 3 is 3, 1 times 3 is 3, and this will become a negative 9. Now I can add row 2 to row 1 so that I can reduce this value here to a 0. 0 plus 1, which is 1, 3 plus negative 2, which is 1, 3 plus negative 3, which is 0, and negative 9 plus 0, which is negative 9. So I'm just going to rewrite our matrix over here. So we need to get this 1 to become a 0, this 3 to become a 0, and this 3 to become a 1. So anytime I want to make something a 1, I multiply by its reciprocal. So here, 3 times 1/3 would give me 1. So I'm going to do 1/3 times row 2. Now I have a 1 here, which is what I needed, and there are 1s all along the diagonal once again. So let's rewrite the matrix. So what I'm going to do is take row 3 and multiply it by a negative 1. So that I get a negative 1 instead of a positive 1 here, and then I can add row 3 to row 2 in order to reduce this value here down to a 0, but not affect any of the other values because I would just be adding zeros. So we'll do negative 1 times row 3, then add row 3 to row 2. So when we multiply row 3 out by a negative, we'll just get a negative 1 here, the zeros will still be 0, and this will be a negative 2. When we add these values to row 2, row 3 stays the same, but row 2 will become 0 plus 0 is 0, 0 plus 1 is 1, negative 1 plus 1 is 0, and negative 3 plus negative 2 is negative 5. Now, all we need to do is reduce this last 1 down to a 0. So what I'm going to do for that is multiply row 2 through by a negative 1 so that I can add it to row 1. So I'm going to multiply row 2 through by a negative, then add row 2 to row 1. So rewriting the matrix that we currently have, so 0 plus 1 is 1, negative 1 plus 1 is 0, 0 plus 0 is 0, and 5 plus negative 9 is negative 4. Now all we need to do is convert these negatives into positive ones. So I'm going to multiply row 2 and row 3 by negatives. So negative row 2 means negative 1 times row 2. Negative row 3 means negative 1 times row 3. All the signs are going to flip. This becomes a positive, this will become a negative, this will become a positive, and this will become a positive. Now let's write our final matrix down. This is reduced row echelon form, where we have 1s along the diagonal and 0s below and above our matrix. Now let's convert it back to a system of equations. Recall the same way we did this with Gaussian elimination, the first coefficient here corresponds to x1, the second coefficient x2, and so on. So we have a 1x1, the rest of these are 0, equals negative 4. So here we have 0x1, 1x2 equals negative 5, 0x1, 0x2, 1x3 in the last equation equals a 2. Now if you recall that with Gaussian elimination, we didn't have zeros above the diagonal, so we still had coefficients there. And we ended up solving for x3 directly, then back substituting it into the other two equations in order to solve for x1 and x2. Putting your matrix into reduced row echelon form with the Gauss-Jordan method, you automatically are obtaining the answers and you don't need to do back substitution. Otherwise, both methods, Gauss-Jordan and Gaussian elimination, should give you the same answer. Now I want to talk about the rank of a matrix. The rank is an important characteristic of a matrix. It's usually denoted by rank of A, where A can be any matrix, like the one we have up here. The rank of a matrix can have many definitions, one of which is dimensions that the columns of the matrix are spanning. To find the rank, you first have to have the matrix in row echelon form. It doesn't have to be in reduced row echelon form. Note that the maximum rank you can have is the lowest number of rows or columns. So, for example, say I have a matrix, an n by m with n being the rows and m being the columns. So we have 2 rows and 3 columns. The maximum rank I can have is either the number of columns or the number of rows, whichever is lower. I have 2 rows and I have 3 columns. The rows are less than the columns, therefore the maximum rank I can have is 2. But now to find the rank, we have to see how many linearly independent rows we have. So let's talk about linear independence. What that means is no 2 rows should be multiples of one another. For example, if I had 1, 2, 3 and 2, 4, 6, if all of these numbers were multiplied by 2, we would obtain the row 2, 4, 6. If I had 1, 2, and if I multiplied all of these rows by 3, I would obtain 3, 6, and 18. Therefore, for both of these examples that I just put up, the second row is a multiple of the first. Therefore, they are not 2 different linearly independent rows. They're just 1. So the rank of these matrices would both just be 1 because there is only one independent line. So if we look at the matrix 5, 2, 3, 2, 6, 1, there are no constant values that I can multiply by to change row 5, 2, 3 into 2, 6, 1, or vice versa. So both of these rows are linearly independent, therefore our rank is 2. So you usually do look at the rows. However, if you have a matrix that looks like this, and in this case, the columns are the smaller value, so you would be comparing columns 5, 2, 3 and 2, 6, 1 to see if you can multiply a constant by this column in order to obtain this one. So when we talk about linearly independent rows or columns, it doesn't always have to be rows that are multiples of one another. 2 rows can also be added together to make a third row, and that third row won't count for linear independence. So for example, say we have the matrix 2, 3, 5. So none of these rows are multiples of one another. There's nothing we can multiply any of these numbers by to obtain one of our other rows. However, if we add together row 1 and 2, we will obtain row 3. 2 plus 2 is 4, 3 plus 1 is 4, and 5 plus 4 is 9. So row 3 is not linearly independent. Just the first 2 are. So when checking the rank of a matrix, you should always check whether any rows are multiples of one another, or whether any of the rows have been added together to make a third. If we call this matrix B, the rank of B is equal to 2. Next, let's talk about the pivot of a matrix. So let's say we have a matrix A. This is a matrix in row echelon form. A pivot is the first value in each row that is not a 0. So starting with row 1, there's a 1 here, and you read left to right. Starting with row 2, left to right, there's 0, 0, then 1. That's the pivot. 0, 0, 0, and 1, that is the pivot. And the last row has no pivot. So these 3 ones are the pivot positions of the matrix. Pivot positions. Note that pivots do not always have to be 1. In this case, they were all 1s, but they don't have to be. Let's talk about the different ways that we can view a linear system. A linear system is basically a set of equations with more than 2 variables. We can have 3y plus 2x equals. This is a linear system. There's a different way that we can view this though. Put all the x's, z's, y's, and constants in separate columns. I'm going to move all of the x values in each equation to the very left. So here we have 2x. I'm going to put y next, plus 3y. And I'm going to bring the 5z over, so the right side is only constants. Plus 5z equals 0. Next, we have negative 3x, just bringing that to the front, plus 2y plus 0z, just as a placeholder because we don't have any z's in the second equation, equals 4. Then we have 3x minus 4y plus 1z equals 6. Now, you may have seen this, ax equals b, regarding matrices. This is a different way to write out a system of equations. So let's go through how we can convert this form to ax plus b form. B is a vector of all of your solutions. The solutions being the right-hand side of the equation, the constants. That's why you have to rearrange your equation to look like this first. All the x's are in one column, the y's in another, the z's in another, and the constants on the right-hand side. So the constants are going to go in their own vector like so. A is all of the coefficients. This x just means all of our variables in one vector. The variables we have in this system of equation are x, y, and z. So they are going to be a column vector, x, y, z. Now, we're going to look in each column to make this matrix. Looking down this column, let's take the coefficients in front of the x, 2, -3, and 3. We are going to put those down here. The next one is row y, 3, 2, and 4. And the last one is row z, -5, 0, and 1. Now, this system of equations is written in the form ax equals b. So if you were to convert this back into the system of equations, you would have to read it row-wise here. So 2 times x plus 3 times y minus 5 times z will give you 0. Then, -3 times x plus 2 times y plus 0 times z will give you 4. Then, 3 times x plus, that's a minus 4 times y plus 1 times z will give you 6. And that is how you would convert this form back into a system of equations. But let's recap what we talked about. Linear systems with ax equals b form, pivot positions, rank, linear independence, and ways to check for it. You need to check linear independence in order to find the rank. You need to check for multiples, where one row might be a multiple of another, or addition, where 2 rows added together might give you a third row. These would not be independent. We also talked about Gaussian and Gauss-Jordan elimination, as well as row echelon form used with Gaussian elimination and reduced row echelon form used with Gauss-Jordan elimination. So that's all we're going to talk about for today's video. If you have any questions, leave a comment below, or go check out the stemtutor.org for more information. Bye for now.